Good morning. We're going to get started. Please take a seat. And to start, we're going to have Elizaveta Shashkova talking about debugging. Thank you.
Hello, my name is Elizaveta Shashkova, and today I'm going to talk about some new opportunities that appeared in Python 3.6 and allowed us to make debugging in Python 3.6 faster and better. And first, let me introduce myself. I'm a software developer of PyCharm IDE at JetBrains company. I'm working on Debugger, and I've come here from the Russian city, St. Petersburg. When we write programs, we always introduce bugs into them, unfortunately. And there are different ways to find these bugs. Some people like quick solutions like adding print statements. Other people prefer logging. In fact, it's the same print statements, but with ability to configure it. But there are a big group of special tools to find bugs in your program, debuggers. Debuggers are much more powerful than just print statements and logging, because they allow you to pause the program in some place. They allow you to inspect the variables values. They allow you to execute stepping commands and monitor the program execution line by line. But if debuggers are so cool, why there are still people who prefer print statements and logging to debuggers? What's wrong with debuggers? The answer is quite easy: their performance. On average, in big real-life programs, it's 30 times slower to run program under debugger written in Python to run it without debugger. And I think it isn't breaking news for you, because everybody knows that debuggers slow down program execution. But why does it happen? And what can we do with that? Today, in my talk, I'm going to answer these questions. We'll learn how to build Python debugger, what problems it might have, and how Python 3.6 can help us to build the faster debugger. Let's start with tracing debugger. It's named tracing because it's based on the standard Python tracing function. Python provides a way to set the system tracing function in order to monitor program execution. This tracing function takes 3 arguments: frame, event, and arg. Frame is frame object, which contains the information of some program point, contains the values of local and global variables, information of code object, function name, and something like that. Event is a string which represents the event which appeared in the program, and argument, the argument of this event. Let's define very, very simple tracing function. We just print the line number of from the frame and event which happened in the program. And let's see how it works. We have a very simple function foo, and we defined our simple tracing function. Let's run this Python program. At first, we will receive in the output the event call on the line 1, because we called our function foo. After that, we receive the event line on the line 2, because interpreter executed line 2 in our function. If we continue execution, we will receive events line on lines number 3 and 4, and after that, the output hi Bob appears in the output. If we continue execution, we will receive events line 3 on the lines 3 and 4 again, because we're in a loop. And after that, we receive event line on the line 5 and event return on the line 5. Event return means that we are leaving the current function because we executed it. Okay. Now we know how tracing function works. And now we want to build debugger based on this tracing function. Every debugger consists of 2 parts: breakpoints and stepping commands. Breakpoints are special places in your programs where you want to pause your program. And stepping commands, the user's commands, which allows you to monitor the program execution line by line. Okay. How we can implement it with our tracing function? It's quite easy. Because inside tracing function, we can access to the frame object and to the number of the line where our program is being executed. So it means we can check if our number of our line number of our breakpoint equals the frame line number, and after that we can suspend program, that is run it in an infinite loop to wait for the user's comments, and implement our breakpoints. And for stepping, we can handle the same events like we've seen in our example, and our debugger will be ready. Okay. But as you can see from the example, the tracing function was called on every line of our program. And of course, it makes program execution slower. In such small example, it is insignificant. But what if we consider another example, which does many operations? It calculates the sum of numbers from the 0 to the 7th power of 10. And what will we see? Even if we define a very simple tracing function, which in fact doesn't do anything, it just returns itself in order to continue tracing in the current frame, and if we run it, we can see that it takes almost 1 second to run this program without tracing function. But it already takes almost 7 seconds to run this program with very simple tracing function. And it's a bit sad news for us. And if we, for example, have 3 breakpoints, that means that we need to iterate through the list of 3 elements on every call of our tracing function. And if we define such tracing function and run our program again, it already takes almost 20 seconds to run such program. It's almost 25 times slower. And let me remind you that our tracing function is very simple. This small experiment explains why running program under debugger is slower than just running it without debugger. Okay, now we have a problem. We call our tracing function on every line of our program, and it slows down program execution, but we can't do anything with that because debugger is based on this tracing function. We can't remove it. Okay, let's remember this problem and start another short story about Python 3.6. As I hope everybody knows here, Python 3.6 was released almost half a year ago, and it has many cool features. And one of them is new frame evaluation API. It was introduced in PEP 5.2.3. PEP is a Python enhancement proposal. It's a design document providing information to Python community or describing new feature. And this PEP provides new frame evaluation API. It allows to specify a parent interpreter function pointer to handle the evaluation of frames. Also, it adds a new field to the Python code objects. It sounds really interesting, but a bit tricky, right? In order to understand something tricky, let's consider example. The easiest way to understand it, very simple example. In real life, we need to write this code in C because this API, this is Python C API. So you should either write it in C or in Python, like we do it in PyCharm, and then generate C code. But for better readability, I will use Python in order to make it easy to understand. But in real life, all this code is written in C or in Python. Okay, our simple frame evaluation function. It takes 2 arguments, frame object, which we have already seen in our tracing function example, and exception flag. Okay, inside our frame evaluation function, we can get the function name of current frame and line number of this frame. Let's print this information and return the default frame evaluation function. Because we don't want to change anything, we just want to print something interesting to output. And of course, we need to set our custom frame evaluation function, pass it to interpreter. Okay, let's see how it works. We have a very simple example, 3 functions. The first function calls the second function, and the second function calls the third one. And we set our custom frame evaluation function and ran this program. What will we see in output? Okay, we can see that our custom frame evaluation function was called 3 times. It was called on the line 1 inside function first, it was called on the line 4 inside function second, and on the line 7 in the function third. That's great. That means that our frame evaluation function works. And it was executed while entering every new frame. And inside this frame evaluation function, we have access to the frame object, and therefore to the code object of the current function. Okay, great feature, but what can we do with that? As you remember, we had a problem with tracing debugger. We executed tracing function on every line of our program. And we can't do anything with that. Of course, we want to remove it, but after that, our debugger will not work. And the solution that I can see is replace. Let's replace tracing function with frame evaluation function. Let's try to build frame evaluation debugger. That is, debugger based on our custom frame evaluation function. As you remember, every debugger consists of 2 parts. At first, we need to implement breakpoints. But when we had tracing function, we had a whole instrument in order to monitor program execution line by line. We had tracing function, it was called on every line of our program, and it was okay. But in this case, we don't have access to any tracing function. We have just a frame object and code object of this frame. How can we implement our breakpoints? Okay, we need to insert our breakpoints code into frames bytecode. And what does it mean? For example, we have function maximum, which returns the biggest value of 2 variables. And let's assume that we want to call breakpoint, to put breakpoint on the line 3. That means that we want to call some function breakpoint on this line. That is, we want to insert call to this function, and the resulting code of this function will look like this. So we call our breakpoint function. It contains some infinite loop where our program suspends and waits for users' comments. So, but we need somehow to implement it. Okay, we can achieve our purposes by bytecode modification. Python bytecode is really easy thing. Python has a very cool standard module named dis. It returns bytecode in a human-readable format. For example, for our function maximum, bytecode will look like this. This is bytecode generated for line 2, this is bytecode generated for line 3, and this is bytecode generated for line 5. You can see that there is no bytecode generated for line 4 because the if-else statement was replaced with this pop jump if false operator. Okay, this bytecode, it looks a bit tricky, but in fact we're not interested what's going on in this bytecode because for us it's just this sequence of operations. Each operation has an offset, these even numbers in the second column, and argument, absolute or relative jump. For example, here, this operator pop jump if false has an absolute jump to the operator with offset 12. You can see it has argument 12. And it, in fact, has link to the operator load fast with offset 12. And if we want to insert breakpoint into this code, what can we do? We can just take bytes of our breakpoint function, take the original bytes and insert breakpoints bytes into the original code's bytes. But we can't just do it because, as I've already said, we have arguments. And when we insert these bytes, all offsets after the insertion will be increased. All these operations goes down, and we need to update these arguments, absolute and relative jumps, in order to our code works fine. So, in order to do our bytecode modification, first of all, we need to insert breakpoints code, and after that, we need to update arguments and offsets in order to make it work. I know it looks a bit scary, but in fact, it's just 200 lines of code in Python. It isn't very difficult. We should just write it very, very carefully. Okay, we know how to insert breakpoints, but we don't know what to insert. And of course, we don't want to insert many, many lines of code, some import statements, global variables. We want to insert some small piece of code. And we can wrap our function with some wrapper function named, for example, breakpoint. This breakpoint function calls stop at break function inside. And inside this function, we can do anything we want, import our util modulus for debugger, and do anything we want. But the original function, breakpoint, it has a very simple bytecode. It's shown on the right. And it just calls the global name of the function and calls it. That's great. We just need to update the globals dictionary of our frame, global namespace, and after that, we will be able to call this function. Okay. Our breakpoints in frame evaluation debugger are ready, and we also need to implement stepping. There are two ways to implement stepping. Of course, we can insert temporary breakpoints on every line, and just when user executes stepping comments, we just can check, should we stop at this line or not? But in this case, we will return to the previous situation, when we had function which we called on every line of our program. And as we remember, it slows down program's execution significantly. So we don't want to use this solution. We want to use another solution. We will reuse all tracing function for implementing stepping comments. If user just executes stepping comments, we set the tracing function just for the current frame and execute stepping comments like we did it in tracing debugger. And when users wants to resume program, we remove this tracing function and continue execution of our program without it. So it doesn't affect performance. Okay, our breakpoints implemented, our stepping comments implemented. That means that our frame evaluation debugger is ready. And let's see how it works. Do you remember this example when we calculated the sum of numbers? And as you remember, it took the program became 25 times slower when we executed it with tracing function. But what about frame evaluation? Yes, it's almost as fast as running without debugger. It happens because it doesn't call tracing function on every line of the program. We just called our frame evaluation function just once when we entered the calculate function. We inserted our breakpoints, and that's all. We didn't do any additional steps, additional calls, so our program runs fast. That's great news. But what if we modify our example? In the previous example, we enter just one frame. But what if we enter frames many, many times? If we define function foo and call it on every step inside our loop, what will happen in this case? In this case, frame evaluation debugging becomes slow. Of course, it's evident because now we enter new frame many, many times. On every entering, we call our frame evaluation function, and it slows down program execution again. What can we do with that? Maybe PEP 523 can help us again. Yes, as you remember, PEP 523 consists of two parts. And the second part of it is that the new field, coextra, was added to the Python code object. It's a special scratch space to use it inside frame evaluation function. And how can we use it in our debugger? We can mark frames without breakpoints. And after that, inside our frame evaluation function, first of all, we can check the value of this co-extra field. And if we already visited this frame, and if we already marked it as visited and marked it as frame without breakpoints, we can quickly check it, and now we know that there is no need to do any additional checks, iterate through breakpoints, do something like that, and we can quickly return default function and skip this frame quickly. Now it helps. Let's see. Yes, we were right. After that, debugging becomes faster in all cases because we don't depend on such situations like in example 2. I want to emphasize these two important features again. Our custom frame evaluation function allowed us to get access to the frame object and to the code object and insert breakpoints right into frames code. And additional co-extra field allowed us to cache frames without breakpoints and skip them very, very quickly without iteration through breakpoints. Okay. Our frame evaluation debugger was implemented, and it works very good in such a small toy example, but what about real life? How about real-life example? Yes, real-life example exists. Frame evaluation debugger was implemented in PyCharm 2017.1. It's available also in PyCharm Community Edition, which is free and open source, so everybody can download it, install it, and try how it works. It isn't just a prototype, but a real thing which works in production. And of course, we made some measurements for PyCharm's debugger too. This is results for one of our benchmarks when we add breakpoints to the global namespace and to the local inside functions. And we compared frame evaluation debugger with our all tracing debugger. Also in all tracing debugger, we had some Python speedups. We rewrote some bottlenecks of our debugger. Debugger's bottleneck, as you can see, a tracing function. It was rewritten with Python, which generates C code, and it made debugger faster. But as you can see, it made debugger 2 times faster. But when we implemented frame evaluation function, debugger became even 40 times faster. The only thing that I can say after that is frame evaluation rocks. It gave opportunity to dramatically improve debugger's performance. And of course, it has some disadvantages. Because such debugger a bit more complicated, because you need to implement bytecode modification, to write all this stuff. Tracing function is much more easier. You can just simply type it and your debugger is almost ready. But for frame evaluation debugger, you need to implement more different things. Also, it's available only for CPython yet, because PEP 5.2.3 was implemented only in CPython yet. And it's available only in Python 3.6, because frame evaluation API appeared just in this version of Python, and it isn't available in the previous versions of Python interpreters. So I can say that frame evaluation function is yet another reason to move to Python 3.6. Most likely, such quick debugger can appear in many other IDEs, many other developer tools. For example, it's going to appear in PyDev, the Python IDE for Eclipse. And also, you might be inspired by my talk, and you might find yet another use cases for custom frame evaluation function. I believe that such use cases exist because when we use it, in fact, we're inserting breakpoints right into code. And that's how we use frame evaluation function for debugging. But originally, this PEP wasn't created for debuggers. Originally, it was created by authors of Microsoft Pigeon project. It's a just-in-time compiler for Python. And originally, this frame evaluation function is used to generate JITed code for frame. And it is stored in this co-extra field of the frame. And Debugger wasn't the original purpose of creation of this API. Just-in-time compiler and debugger are quite different instruments, but they use the same API. So I believe that other use cases definitely exist. We just need to think about them and just need to create them. For example, we can just imagine, just like an idea, as I already said, we insert breakpoints inside our code. But for example, we can add, I don't know, logging right into our code. Just imagine you can insert logging statements without modifying your source code. You just defined your custom frame evaluation function, which adds logging for some functions, and you can quickly turn it on, turn it off by adding just one line inside your code. That sounds really good. Okay, if you want to try it, frame evaluation debugger, or watch the whole code base of today's examples, you can check out my repository on GitHub. It's a small prototype of frame evaluation debugger. And also you can check the source code of PyCharm Community Edition. As I've already said, it was implemented and it works. So you can see its code and ask me any question. Also, feel free to follow me on Twitter. And I'm ready to answer to your questions, but I think it's better to ask me them personally. Today, all day, I will be available at JetBrains booth in Expo Hall. So feel free to find me. Feel free to ask me anything. I like questions very much. And thank you for your attention.